Okay, we're going to start going through the Electrostatics study guide for our test coming up on Thursday. So, all right. Number one, oops, I didn't mean to go that way. Okay. We've got a neutral balloon rubbed against neutral fur, and the balloon's going to become negatively charged. So we've got our balloon, we've got some fur, and this is just like what we did in class where we rubbed the balloon with the felt, okay? The balloon is going to become negatively charged. That means it's going to gain some electrons from the fur, okay? The fur is going to lose some electrons to the balloon. So which charging method is described? This is friction, where you rub two objects together. And what charge motion is responsible for the fur becoming positive? That would be electrons moving. So electrons are moving from the fur to the balloon. And we know that electrons are the only particles that move, right? The protons are stuck in the nucleus. They can't move. So when we do any of these charging methods, it's only the electrons moving, okay? So what this is going to do is leave the fur. It leaves the fur with more protons than electrons because the fur is losing some electrons to the balloon. The balloon is picking those up and becoming negatively charged. All the protons in both of these are staying put. It's just electrons moving around. Okay. Positively charged glass rod. So this is a glass rod that has lost some electrons. So it's got more protons than electrons. It's brought near a neutral metal sphere. Okay. So what we want to do here, first of all, is draw in negative charges so we can make this sphere look neutral. Okay. We also want to draw them in the location they would be because of this positively charged rod being brought nearby. So when we bring this near, okay, this is induction where we're not touching these objects. And when we bring this one near our neutral sphere, our negative charges are going to want to come over and be near the positively charged rod because they're attracted to it. So we're going to draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 negatives here collected on this side because they're all going to wander over here close to this positively charged object because they're attracted to it. Okay, so my sphere is still neutral because these two aren't touching. They're not transferring any electrons between them. They're just, this is causing my charges in my neutral object to move around. And that separation of charges is called polarization. So that's one of our, we've had a lot of vocabulary terms in this unit. And that's one of them is when our charges are separated from each other into positives on one side, negatives on the other. That really just means electrons have moved from one side to another. And so I have more electrons here, I got less electrons here. And that's called polarization. Okay, so here we've got two protons and then an electron. And it says, what is the direction of the net force, if any, on the electron? Okay, so this is where we're going to think a little bit about Coulomb's law. Let's see, let's write that somewhere so we have it handy. Remember, Coulomb's law is our constant that we're not concerned about times a value of one charge times a value of another charge divided by the distance between them squared. Okay. So in the case of these particles here, my electron is closer to this proton than this one. So my net force is actually going to be in the direction of this proton. So it's going to be like so, because this distance is greater than this distance. And remember, if distance goes up, force goes down. So let's jot that down. Remember, they have an inverse squared relationship because of this equation here. Okay. So since this distance is bigger than this one, the net force is going to be stronger towards this proton. So we can just draw that arrow for our force. And this is just, I don't know, kind of a pictorial way of thinking about these relationships in the electrostatic force equation. Similar here, except these two distances, to me, they look the same. They look like the electron is the same distance apart from both of these protons. So these force vectors, I'm going to draw the same. Okay. Same distance here for both protons. So we're going to have the same force value because these are all, the same charge values. Like these two are the same. And then these distances look like they're the same here. Okay. Again, just another pictorial version of what we were talking about with the electrostatic force. Okay. Object A attracts object B. Object B repels object C. And object A repels object D. Object B is negatively charged. What is the charge of object D? Okay, so let's kind of draw this out. Right, so we've got A, and A attracts B. So A and B like each other. So that tells us they must have opposite charges. Then B repels object C. Okay, it doesn't want C near it. And then A repels D. Okay, so they tell us that B is negatively charged. Okay, so B is negatively charged. That means A has to be positively charged because these two are attracted. Okay, so then that would tell us if B repels C, C must be negative because they would be like. And if A repels D, then D must be positive because they would be like. Okay, so D is going to be positive, positively charged. So we just kind of went through a little, first a sketch there of attracting and repelling, and then we're just using the opposites attract and like repels, okay, reminding ourselves that if we've got two negatives or two positives, they're going to repel each other because they don't have anything that the other wants. Whereas with opposites, you've got one that has less electrons, one that has more. Their tendency is going to want to be to transfer electrons to correct that imbalance. So you end up with opposites attracting. Okay, so two balloons hanging from the ceiling appear to repel. So say we've got two balloons in our classroom and they are repelling each other. So why would they be repelling? It's because, like we just said, they must be charged in the same way. They could be positively charged or they could be negatively charged, but they're both the same. And that means they don't want to be near each other. That means they repel each other. Name 2 ways a student could get the balloons to repel with more force. So going back to our electrostatic force equation, 2 ways we could increase our force. We could increase our charge, so we could rub those balloons more with felt, get them even more charged up. Or we could decrease our distance. We could bring them even closer together. If we do that, they should repel even more. Okay. So increase charge and decrease distance. Okay, both of those are going to increase this force value. If we increase one or both of these are direct relationship with this. That's going to cause this to go up. If we decrease this value, we're dividing by a bigger value. Okay. If we decrease it, then we're dividing by a smaller value, and this number is going to go up. Okay. If your objects are farther apart, they can't exert as much force on each other. So, we want to increase the force, we got to decrease that distance. Okay. Okay, I think I got time for one more in this video, and then we'll stop. 2 similarities and 2 differences between gravitational and electric force. So remember when we talked about electrostatic force, we also spent a bit of time comparing that back to our force of gravity, just because these equations are so similar. Here, instead of charge, we have masses divided by distance between them squared. Okay. So how are they similar? How are they different? Okay. One big difference is that electrostatic force can attract or repel, and gravitational only attracts. Remember we said that we've been saying opposites attract, like repel. So your electrostatic force, you can have 2 like charges that repel, or you can have 2 that attract. With gravity, everything that has mass attracts everything else with mass. So it only attracts. Okay. Another way they're different is the equations include different variables on the top. We've got charge in the electrostatic force equation. We've got mass in the force of gravity equation. So we'll just say charge, because I don't have a lot of room to write here. Charge versus mass. Okay. 2 similarities. The big similarity is that both of these have an inverse square relationship with distance between either my charges or my masses. Inverse square relationship with distance. Another similarity, these are both fundamental forces of the universe. Remember that electrostatic force is a lot stronger than gravity. But I mean, they're both in that list of the really important key fundamental forces. Okay. Okay, I'm going to stop there because this video's gotten kind of long and continue with the next one.